Hi everyone, my name is Laura Karan, and this research grant proposal has been developed for funding and approval of long-term post-fire monitoring of soil moisture in the active layer of permafrost regions across the central and eastern Canadian Arctic. As the Arctic warms faster than any region on Earth, major changes are taking place on land, and one of the most striking is the thawing of vast regions of permafrost that have underlain these polar regions for hundreds of thousands of years. If the Arctic continues to warm as quickly as climatologists are predicting, an estimated 2.5 million square miles of permafrost, accounting for 40% of the world's total, could disappear by the end of the century. Despite the long, severe winters and relatively short summers, wildfires do occur and are a part of the natural ecosystem of the Arctic. While tundra fires occur infrequently due to the lack of vegetation to burn in the rocky or sparsely vegetated alpine tundra or the wet coastal plains, it can happen under the right conditions. The most frequent and largest fires occur in forested areas and in the interior lightning belt, where fire is a significant natural process. Fire also plays a key role in the regulation of the permafrost table throughout this area. Without fire, organic matter accumulates, the permafrost table rises, and ecosystem productivity declines. Vegetation communities become less diverse, and wildlife habitat decreases. It is fire that rejuvenates these systems. However, the Arctic is currently being set ablaze. Fires have raged in the boreal forests of Greenland, Russia, Alaska, and Canada in the recent years. Though fires are a natural component of all these ecosystems, to see them on this scale in the Arctic is unprecedented and highly unusual. Shifts in fire return intervals can be attributed to increased heat drying the soil and melting the permafrost. But there are also more surprising reasons too, such as the warming climate is leading to more lightning strikes, which are causing even more forest fires. The effects of wildfire on surface and ground temperatures are devastating, and in much of the peatland are dominated by flameless, smoldering combustion, which move overland through the leaf litter at a pace of about half a meter a week, rather than the speedy rate of an average 10 kilometers per hour in a forest fire. These smoldering fires not only are ignited much more easily than fiery flames by lightning strikes, but they can also persist through cold and wet conditions much longer, largely because the peat holds vast stores of combustible gas methane. As the climate warms, northern soils and peat dry out, making smoldering fires much more likely. These smoldering fires are actually a much greater threat to global climate. They burn for much longer, so they can transfer heat much deeper into the soil and permafrost, overall consuming twice as much carbon-rich fuel as normal fires. Capable of smoldering beneath the surface, these subterranean fires can persist through the winter and pop up in spring in completely unexpected locations, hence their nickname zombie fires. Loss of permafrost in the southern limits of the permafrost zones, as well as widespread subsidence, has also become a serious problem. Subsidence is causing a whole host of issues, ranging from instability of soils to altered hydrology and increased topographic variation through changes in geomorphology. Compounded cascading effects of climate change and wildfire are also adversely affecting the active layer thickness. It is climate change and topography which are the greatest causes of the heterogeneity and patchiness of permafrost, and therefore in many areas the lack of a continuous permafrost zone is expanding. Permafrost is a permanently frozen layer on or under Earth's surface. It consists of soil, gravel, and sand, and is usually bound together by ice. It usually remains at or below 0 degrees Celsius for at least 2 years or more. The thickness of it can range from 1 meter to more than 1,000 meters, and it covers approximately 22.8 million square kilometers in Earth's northern hemisphere alone. There are two major ways to describe permafrost distribution: continuous and discontinuous. Continuous permafrost is a continuous sheet of frozen material. Discontinuous permafrost is broken up into separate areas. Some permafrost in the shadow of a mountain or thick vegetation stays all year. In other areas of discontinuous permafrost, the summer sun thaws the permafrost for several weeks or months. Studies show Earth's permafrost warmed by about 6 degrees Celsius during the 20th century alone. Scientists predict widespread thawing of permafrost by the year 2100. With climate change, wildfire frequency and severity are expected to increase. The fire itself doesn't melt permafrost directly, but rather a blaze will eradicate vegetation, which reflects and absorbs sunlight. When that insulating layer is lost, the ground heats up more readily, causing permafrost to thaw. Initially, permafrost thawing will bulk up the active layer, which is the layer above permafrost that freezes and thaws seasonally. And in turn, it will temporarily provide an additional amount of thermal insulation against further thawing. However, with rapid warming and increased fires, the temporary buffer in the feedback loop will only decrease in the time felt and the lag will lessen. Much of the ongoing research in the world in this discipline has primarily been conducted in Siberia, Alaska, and Western Canada. There is currently a major gap in the existing body of research that desperately needs to be filled. Soil moisture is vitally important in the discussion of wildfires' effects on the Arctic. Soil moisture, sometimes also called soil water, represents the water in land surfaces that is not already in rivers, lakes, or groundwater, but instead resides in the pores of the soil. The level of soil moisture is determined by a range of factors beyond weather conditions, including soil type and associated vegetation. In turn, soil moisture levels affect a range of soil and plant dynamics. The active layer is the portion of the soil above permafrost that thaws and freezes seasonally. It plays an important role in cold regions because most ecological, hydrological, biogeochemical, and pathogenic activity takes place within it. Changes in active layer thickness are influenced by many factors, including surface temperature, physical and thermal properties of the surface cover and substrate, vegetation, soil moisture, and duration and thickness of snow cover. Cryosols are widely known as permafrost soils. A cryosol soil can be defined as having one or more cryotic horizons within 100 centimeters from the soil surface. Gelisols are another name for cryosols and are divided into 3 suborders: distols, turbels, and orthols. Most gelisols store large quantities of organic carbon. Only soils of wetland ecosystems contain more organic matter. Among the many threats that permafrost loss due to climate change and an increase in wildfire frequency poses is perhaps the most alarming. The shift from serving as a carbon sink to a carbon source, as the melting and receding areas falling within the permafrost zone are releasing massive quantities of both CO2 and methane. Methane is a potent greenhouse gas, trapping 86 times more heat in the atmosphere than carbon dioxide. In fact, nearly 20% of the plant's warming can be attributed to methane. There are an estimated 1,400 gigatons of carbon frozen in permafrost in the Arctic, making it one of the largest carbon sinks in the world. That's about 4 times more than humans have emitted since the beginning of the Industrial Revolution, and nearly twice as much as is currently contained in the atmosphere. As a research goal, my team will aim to prove that the depth of thaw penetration and active layer thickness will both increase given the effects of climate change and shifts in the fire regime of the permafrost regions of central and eastern Canada. Additionally, surface soil organic matter and peat will serve as a temporary insulator in the instance of temperature increase, but will increase the burn severity of wildfire due to the direct effect on surface and ground temperatures provided by these additional fuels. The area of interest for the proposed study to be conducted in is the extensive, discontinuous, and sporadic discontinuous permafrost regions of central and eastern Canada above 55 degrees north latitude and between 60 and 110 degrees west. This will include sample sites across numerous provinces, to include eastern portions of the Northwest Territories, Nunavut, Saskatchewan, Ontario, Quebec, and portions of Newfoundland. Site analyses will occur throughout the study region at various transects which cross the boreal, subarctic, and Arctic ecoclimatic provinces. Sites will be designated on the basis of vegetation and surficial materials in the representative undisturbed areas. Site variability will be investigated using soil probes with data loggers to collect temperature readings and thaw depth penetration. 2-meter by 2-meter sample pits will be dug to examine soil profiles at each site. Additionally, soil cores will be collected with thaw tubes. Further data will be collected utilizing the extensive network of GPS stations already in place across Canada. These GPS stations were originally designed and maintained for tectonic and ionospheric studies. However, the use of a relatively new technique known as Global Positioning System Interferometric Reflectometry, or GPSIR, will aid in gaining information about subsidence and topographic variation. GPSIR uses reflected GPS signals to measure surface elevation changes to study frozen ground dynamics. This type of study has only previously been conducted in Barrow, Alaska, but we would like to adopt this technique. Core sample data, climate data, and topographic variation will be cross-referenced, similarly to how data collected by dendrochronologists is cross-referenced through descriptive and inferential statistical analyses. Upon completion of this study, our team will put together a peer-reviewed journal article and will submit it to various academic publications as it relates to the various key topics encompassed within the body of research. The data we have collected will serve to augment the Canadian government and Natural Resource Canada's existing body of research from Western Canada to create a more inclusive database of climate change impacts. Efforts of this study will collaborate with the permanent research team currently established in the Mackenzie Delta near Inuvik, Northwest Territories, to provide raw GPSIR data for GIS mapping purposes. We also would like to lobby for the establishment of more long-term research facilities throughout Central and Western Arctic for data collection teams. Thank you all for listening, and I encourage you to explore more information from our research partners at the Aurora Research Institute in the Mackenzie Delta Permafrost Research Team. Thanks!